Hello students. Today in our science class we will be talking about the mirror and lens formula. Also we will be talking about magnification and then various cases of refraction of light. So let us immediately start. As you know, some topics we have already covered in the earlier session. Today we will be starting with mirror formula. So what is mirror formula? If in case of a spherical mirror, the distance of the object from the pole is taken as u, distance of the image from the pole of the mirror is v, and the distance between the principal focus and the pole is considered as f, then the mirror formula is given by 1 upon u plus 1 upon v is equal to 1 upon f. So students, this is a mirror formula. Now, how do we use mirror formula? Mirror formula is generally used to find out the focal length of a given mirror if in case you know the object distance and the image distance. It can be also used to find out object distance if in the case object is too far, too away from you, then you can use this formula to find out the object distance also. For example, a distant star. A distant star, you cannot measure the distance, right? So you can use this formula to find out the object distance. That is how far that object is from you. Provided you have, or you can say you know, the image distance and the focal length of the given mirror. So that's how we use mirror formula. Students, please note that we must use Cartesian sign conventions while substituting the numerical values of object distance, image distance, or focal length. You already know the sign conventions because we had studied this in the earlier session. If you have not watched the earlier session, please do watch it. I will post the link of part number 3 of the light in the description box. So, the next topic is magnification. What is magnification? Magnification is produced by the spherical mirror. It gives the relative extent to which the image of an object is magnified with respect to the object size. So what does it give you? It gives you the extent to which the image has been magnified with respect to object. So that is your magnification. It is expressed as the ratio of height of the image to height of the object. So when you find out the ratio of height of the image to height of the object, then you get magnification. Then it is usually represented by the letter m. Okay, so put it mathematically. If we want to express it mathematically, how do we write it? M is equal to, that is magnification is equal to height of the image h dash upon height of the object h. What is h dash? H dash is the magnification, the height of the image. Okay, and what is h? H is height of the object. I repeat, what is h dash? H dash is height of the image, and what is h? Height of the object. So when you take the ratio of these two things, you will get magnification. So h dash upon h will give you m, that is magnification. The next part is magnification is also related to object distance and image distance. Okay, so you can modify our relation as minus v upon u. So this minus image distance upon object distance will give you magnification. So if in case you cannot find out height of the image or height of the object, then you can try out another relation, image distance upon object distance, but you have to take negative of image distance upon object distance. Why negative? Because the while substituting numerical values, image or object, okay, either of the two distances are generally negative. Okay, so and magnification can never be negative. So just to nullify the negativeness, we use minus sign. Okay, so that's the reason why we have put a minus sign, because you know that sign conventions we have to use in the formula while substituting the numerical value. So even if either one of the two, if you get it as negative, then there will be a problem, because magnification is never negative, it is always positive. So that's what you do, you put a minus sign in the relation. Well, let us move on further. Then comes refraction of light. Refraction of a light through a rectangular glass slab, you all have seen. Okay, in our lower grades we have seen refraction of light. So what is refraction? Refraction is nothing but bending of light. When the medium changes, light changes its path. And why does it change the path? Because of change in velocity. Because suddenly the medium gets denser, and then light has to travel little slow than its earlier speed, because there is resistance offered by this dense mediums. So especially when it is a glass slab or water, such dense mediums are there, then light has to change its speed. And when it changes the speed suddenly, there is little bend in the path of the light, provided there is a oblique incidence. Okay, if there is a normal incidence, then it doesn't change its path. I repeat, if there is a normal incidence means what? Perpendicular entry. So if it is entering into the glass slab perpendicular to the surface, then light path doesn't bend. However, if there is oblique incidence, then it bends, and it bends towards the normal. Okay, and later on when it again exits the glass slab, it again bends, it goes away from the normal. So that's how refraction happens in case of glass slab. Refraction is due to change in the speed of the light, like I said earlier also. Experiment shows that refraction of light occurs according to certain laws. And what are these laws? Let us see. The first one, incident ray, refracted ray and the normal, they lie in the same plane, and the ratio of sine of angle of incidence to the sine of angle of refraction is constant. So sine I upon sine R, that is sine of angle of incidence and sine of angle of refraction, the ratio of the two is constant. This law is also known as Snell's law of refraction. Okay, please check or please note the spelling of Snell. It is not SNAIL. It is not that Snell. This is different Snell. This is the name of the scientist, SNELL. Well, provided the angle should be between 0 and 90 degree. So this you have to remember always. Only then you can use this relation. If I is the angle of incidence, R is the angle of refraction, then how do we put it mathematically? Sin I upon sin R is constant. Well, with this we come with another topic, refractive index. We arrive at this particular topic because it is related to Snell's law only. Refractive index is defined as the ratio of velocity of light in vacuum to velocity of light in specified medium. So if c is the velocity of light in air and v is a velocity of light in the specified medium, then refractive index Nm is equal to c upon v. So that's how we put it mathematically. Understood? So Nm is what? Refractive index. It is equal to speed of light in air divided by speed of light in given medium. So if you take speed of light in air as c, velocity of light as v, then velocity of light in specified medium, if you take it as v, then the formula is c upon v. Then comes the next topic, which is absolute refractive index. This Ri stands for refractive index. Students, talking about absolute refractive index is nothing but a comparison of velocity of light in vacuum to that in other mediums. So for example, if the other medium is water, then if you compare velocity of light in vacuum to that of water, okay, that will give you absolute refractive index. So it is different for different materials. So this is a table which I have taken from NCERT textbook. It is very clearly written over there that refractive index of air is 1.0003, then refractive index of I is 1.31, where the smallest refractive index that is very close to the vacuum is air. It is 1.0003, so very close to vacuum, because in vacuum the refractive index is 1. Okay, so it's very close to that. Obviously it will be 1, because velocity of light in vacuum to that in vacuum will be 1, right? So that's how we get refractive indices. So that's why vacuum is obviously 1. Then air, it is 1.0003, very close to vacuum. In fact, while finding out a refractive index, this absolute refractive index, you can use velocity of light in air also, because it's almost same. Okay, very close to that in vacuum. Then the maximum, if you observe the maximum value of refractive index is for diamond, in according to this given list. For diamond it is 2.42, whereas others are comparatively less. For example, for the refractive index, absolute refractive index of sapphire is 1.77, then ruby it's 1.71, so it goes on decreasing until air. For air it is 1.0003. So these are the list of the refractive indices of various materials. Then comes refraction by spherical lens. This is one of the major topics in the lesson light, reflection and refraction, along with the various cases of reflection for spherical mirrors. Okay, for spherical mirrors there are some 6 to 8 cases, 6 for concave mirror and 2 for convex mirror, right? So they are also important, and these cases are also important. But the relieving part for you, relieving part means the one that makes it easier, is it is somehow very close to the 8 cases of spherical mirrors. So whatever cases we have done in spherical mirrors, if you have understood those cases, if you have understood the difference between each cases, then this will be easier for you to learn by heart. Let us see spherical lenses. So, converging action of a convex lens and divergent action of a concave lens. Starting with this is what happens. For convex lens, when light passes through the convex lens, it converges. So, rays of light come together at one single point, which is called as principal focus. Whereas, on the contrary, for a concave lens, the ray of light goes away from its path, it goes away, it diverges. So that's why it is also called as diverging lens, and this one is called as a converging lens. Talking about the refraction by spherical lenses, the nature, position and relative size of the image found by convex lenses for various positions of object are as follows. So this list is also given in your NCERT textbook. Very helpful textbook, students. Please refer NCERT textbooks. Most of the information in these videos are taken from NCERT textbook. I generally refer NCERT because you get all the information of NCERT of the syllabus in these textbooks. Well, when the position of the object is at infinity, the position of the image is at focus. So that's what you have to remember. This is similar to other concave mirror cases. So if the position of the object is at infinity, position of the image is at focus. The relative size of the image is how? It is highly diminished of the point size, and nature is obviously real and inverted. Now, if you bring the object closer, if you put it beyond 2f1, okay, then where will be the position of the image? Position of the image will be between f2 and 2f2. Size will enlarge little bit, but it will be still diminished. Why diminished? Because it is smaller than the object. The nature of the image is real and inverted. Now, if you bring the object more closer at 2f1, then image will be at 2f2. So at the same distance but on the opposite side. The size will be same and nature of the image will be real and inverted. Now, if you bring the object even more closer, if you bring it between f1 and 2f1, then the image will shift farther. So as you bring the object closer to the lens, the image starts going away from the object as if it is scared of the object. Okay, So yes, so if you place your object between f1 and 2f1, then image goes beyond to f2, and then the size of the image increases. Still, the nature of the image is real and inverted. Now you shift the object even more closer. You bring it at f1, that is focus. Then position of the image will shift even further. It will go to infinity. It will be infinitely large, highly enlarged, but it is at infinity. Nature of the image is still real and inverted. Now comes the sixth and the most different case from all other five cases, where the object is between f1 and optical center. So you have brought it so close now that it is between optical center and f1, then position of the image suddenly shifts on the same side of the lens. So earlier it was on the other side of the lens. Now it has shifted to the same side of the lens, and it has become enlarged, but it has also become virtual and erect. So the image suddenly, earlier in all earlier cases it was inverted, here it becomes erect. Also, in earlier cases, it was real. What do you mean by real? You can take it on the screen, but here the image is virtual. So you will not be able to take the image on the screen. So that's how you can learn. That's how why this table is so important. You can learn almost every case from this single table. And if you know this table, please mind that your work is easier, because then you can draw the diagrams, the ray diagrams very easily if you know this table. So please learn by heart this table. It is very similar to the concave mirror cases, the 6 cases of concave mirror. So if you know that the difference between all the cases, then here it will be very easy. And once you know this table, the ray diagrams becomes easier for you, because that is what asked in the exams. Generally, in board exams, ray diagrams are asked. And if you know this case, then drawing the diagram is very easy. Let us move on to some rules. Okay. So, what are the rules? The rules for the cases for concave lenses. So earlier it was convex lens, now it is concave lens. So there are only two cases for concave lenses. It is similar to convex mirror. Convex mirror also there were two cases. Here also there are two cases. So only two cases. Object can be either at infinity or it can be somewhere between infinity and optical center. The only difference you will find is that it was pole, here it is optical center. So if the object is at infinity, image is formed at focus and the image is highly diminished, point size, the image is virtual and erect. That is, you cannot take it on the screen. Also, if the position of the object is anywhere between infinity and optical center, then image is found between focus and optical center. Okay, and obviously the size is, though it is little big, but it is diminished compared to the object, and nature of the image is virtual and erect. Image formation using ray diagrams. So these are the rules. If the ray of light is coming parallel, then after refraction through a convex lens, it will bend its path, there will be a refraction and it will pass through the focus. Whereas in case of concave lens, if the ray is coming from infinity, this parallel lines indicates that the ray of light is coming from infinity, the object is at infinity. So if it is coming from infinity, it will diverge. However, if you geometrically construct the this diverged line backwards, it will pass through the focus. Okay, so that's what happens in case the object is at infinity. Then if the ray of light, there is a oblique incidence and it is passing through the focus, then after refraction it will emerge parallel to the principal axis, and the same thing happens with concave lens also. If there is an oblique incidence, so that the extended line passes through the focus. Then after emerging from the concave lens, it passes parallel to the principal axis. So I will just read out the statement. A ray of light passing through principal focus after refraction from convex lens, it will emerge parallel to the principal axis. So that's what I said. Then the ray of light appearing to meet at the principal focus. In case of concave lens, it will emerge parallel to the principal. So in both these cases, the emerging light is parallel to the principal axis. Then this is same for both convex lens as well as concave lens. If the ray of light passes through the optical center, then it emerges without any deviation. So there is no deviation when light passes through the optical center, and this is true for concave lens also. Now comes the ray diagrams. The 6 cases that we have done for convex lens, those 6 cases can be represented by ray diagram also. So what are the ray diagrams? Case A, where the object is at infinity. So I had said that if the object is at infinity, the ray of light passes through the focus. So the image is formed at the focus. It is real, inverted and highly diminished of the point size. So that's why it is point size, because ray of light are coming together at one single point. Then case number B, where the object is beyond 2f1. Okay, now it has come from infinity to beyond 2f1. So here the image is formed between f2 and 2f2, and relatively it is smaller compared to the object size. The size is smaller, so size of the image is diminished and it is real and inverted, as you can see from the diagram. Then there is a case number C, where the object is brought closer. It is kept at 2f1. So if object is at 2f1, the image will be at 2f2 on the other side of the lens. It will be of the same size. The only difference is it will be inverted image of the object. Then if you bring it even more closer, suppose it is at between f1 and 2f1, then the image will be found beyond 2f2, beyond center of curvature. So it will be enlarged also compared to the object size, but it will be still real and inverted. Then comes case number 5, where the object is at f1. Now if the object is at f1, the image is formed at the infinity. It is too large, it is real and inverted, but it is at infinity. Then the last case, which is different from all other cases, where the object is placed between f1 and optical center. So if object is placed between f1 and O, that is optical center, the image shifts to the same side of the lens. So image will be formed here. It will be enlarged, it will be big, but it will be virtual. Though it is erect this time, but it is virtual. So you cannot take it on the screen. So students, with this we arrive at the second part of the lens, spherical lenses, which is the ray diagrams representing the image formation in case of concave lens. So earlier it was convex lens, now it is concave lens. So let us see the two cases. The first case was the object is at infinity. So if the object is at infinity, the virtual image is formed and it is formed at the focus. So the image is highly diminished of the point size, but it is on the same side of the lens, and this image is virtual. That is, you cannot take it on the screen, because in real life the ray of light are getting diverged from the concave lens. Then there is a second case where object is anywhere between infinity and optical center. If that is the case, then the image is little big than the earlier case, but it is still diminished compared to the object size, and it is formed between f1 and optical center, like you can see it here also. So that are the two cases. These are the two cases of concave lens. So if you know the table, I repeat, if you know the table, it is very easy to draw the ray diagrams. Then comes the sign conventions. But students, the relieving part is the sign conventions are same for lenses also. Just like mirror, the sign conventions are same for lenses. The only difference is that instead of taking measurement from the pole, because here we don't have any pole as such, here we have optical center. the center of the lens. So you take the distances, you measure it from the optical center. So whatever distances we are taking, it might be object distance, it might be image distance, or it can be a focal length. You take it from the optical center. So that is the only difference. The rest of the conventions are same. Then comes the lens formula. What is lens formula? Just like a mirror formula, there is a lens formula where you can find out the focal length using object distance and image distance. I repeat, you can find out the focal length using object distance and image distance, or if you have focal length, if you have object distance, you can find image distance. Okay, or for that sake, you can find out object distance if you know image distance and focal length. So either of the two you should know, either of the three I should say, either of the three, at least two quantities you should know, then the remaining quantity can be easily found out. So if u is the object distance, v is the image distance, and if f is the focal length, then 1 upon f is equal to 1 upon v minus 1 upon u. Students, you might have noticed that it somehow resembles the mirror formula, but the difference is that it was plus 1 upon u. So here there was a plus sign in mirror formula, whereas in lens formula there is a minus sign. Okay, there is derivation, but derivation is not for you at your level. When you will go in higher grades, you will get derivation of these formulas also. Well, with that we arrive at the another topic, magnification, which was there for mirror also. So here also there is a formula, magnification produced by lens. So how do we calculate magnification? The process is same. You have to find height of the image to height of the object. Okay, so no difference in that. Magnification is same formula, height of the image upon height of the object. Okay, but if you want to use object distance and image distance, then it is different. Then it is v upon u. Instead of minus v upon u, which was there for mirror formula, here it is plus v upon u. Okay, so that is your relation for magnification. And the last part, which is power of the lens. So how do we calculate power of the lens? First of all, what is power of the lens? The power of the lens is defined as the reciprocal of focal length. It just gives you the capacity of a given device to magnify certain thing. Okay, so it is represented by the symbol p. P is equal to 1 upon f. So that is a mathematical relation to find out power of the lens. So since it is reciprocal of focal length, the unit will be meter inverse. But instead of using meter inverse, what we use is diopter. So 1 diopter is equal to 1 meter inverse. That you have to remember. So that was all for today. I hope you understood each and every part of the lesson. If you have any doubt, feel free to ask. You can put your comments in comment box. The homework for you is you can try to solve numerical values, numerical problems or numericals from the lesson. Okay, there are few numericals especially related to magnification part or power of the lens. They're easy. You can try to solve them, but I'm saying trying because I'm going to come up with the videos for problem solving also. I'm going to make the videos for especially for problem solving, so you can wait for that, but until then you can try also some numericals at least, which are direct, almost directly using the formula, substituting the values. That way also you can do. Okay, so that's it guys. Thanks for watching this video. If you have any doubt, as I said, you can definitely ask me. You can put your comments in the comment box. So see you during next session with the new topic. Until then, take care. Bye bye.